Hello everyone, I hope you are well. This lesson is about redox reactions, which means electron transfer reactions, which many of them take place in water. Now you can see the combustion reaction of magnesium and oxygen, which leads to the formation of magnesium oxide, and magnesium oxide is an ionic compound. As a precipitation forms a precipitant. If we divide this molecular formula into two sections and write a half reaction, first this reaction which magnesium lose electrons, and this half reaction which oxygen gain electrons. The first one is called the oxidation reaction, in which the electron is lost, while the second one is called the reduction reaction, which electrons are gained by oxygen. So we can say that magnesium transfers its electrons to oxygen. It can be considered as a reducing agent, which means that it donates electrons, while oxygen gains the electrons, which is the oxidating agent. So the compound that gains the electron is oxidating agent, and the element that loses the electron is the reducing agent. There are two definitions for them. Now consider another redox reaction between zinc and copper sulfate. In this case, we can see copper reduces and forms a precipitation. Now you can see that it's brown, while zinc is oxidized and it donates electrons to coppers. Here you can see the molecular equation, the net ionic equation that we talked about how to find them in previous lessons, and the half oxidation reaction in which the zinc donates the electrons, and half reduction reaction in which copper gain the electrons and it forms the precipitate. Okay, here we have a definition which is called the oxidation number. What's that? To keep track of electrons in redox reactions, it is useful to assign oxidation numbers to the reactants and products. An atom's oxidation number, also called oxidation state, here I will write oxidation state, signifies the number of charges the atom would have in a molecule if electrons were transferred completely. Charge of the molecule in the case of electron transfer, a complete electron transfer. Okay, now maybe you have some questions. How we can find the oxidation number? Here there are some rules to find the oxidation number. Number one, it says in free elements each atom has an oxidation number of 0. Thus, each atom in hydrogen, oxygen, sodium, and phosphorus, they have the 0 oxidation number. Number 2 says for ions composed of only one atom, that is monoatomic ions, the oxidation number is equal to the charge on the ion. Thus, lithium has an oxidation number of +1, barium +2, iron 3, and so on, even for the oxygen -2. And in case for group 1, which is alkaline metals, all of them has the +1 oxidation number. Group 2 alkaline earth metals +2, and even aluminum, the group 3, they have the +3 oxidation number. The oxidation number of oxygen in most compounds is -2, but in the hydrogen peroxide and peroxide ions we have an exception, which the oxidation number is -1. The oxidation number of hydrogen is +1, excuse me, except when it is bounded to metals in binary compounds. In this case, its oxidation number is -1, like sodium hydride, calcium hydride. For the halogens, consider that fluorine has an oxidation number of -1 always in all its compounds. Other halogens have negative oxidation numbers when they occur as halide ions in their compounds. When combined with oxygen, they have positive oxidation number. For number 6, it says in a neutral molecule, the sum of the oxidation numbers for a neutral molecule must be 0. In a polymeric ions, the sum of oxidation numbers of all the elements in the ion must be equal to the net charge of the ion. So if we have a compound that doesn't show any positive or negative above, the sum of the oxidation number is 0. In other cases that you see, for example here in ammonium, you will see a positive here. The oxidation number of this compound is +1, so it's not 0. And if we want to find the oxidation number of each of the elements, we have to know. For example, for the nitrogen, the oxidation number is -3. So if we want to find the oxidation number of hydrogen here, we have to write an equation. -3 plus 4x, it could be +1. So if we solve and find the x shows what? +1. So here for the hydrogen, even we have +1, and the total charge of this molecule is +1. Oxidation numbers don't have to be integers. For example, the oxidation number of oxygen in superoxide ions, but of course they don't have to be the integers, but we have some exceptions. For example, here in the superoxide ions, we have the a fraction, so that could be considered as the exception. Here, as an example, assign oxidation numbers to all the elements in the following compounds and ions. Consider that for solving such examples, you have to refer back to the previous table that I have provided, and even at the end of this lesson, in the descriptions, I have provided a table in which there are the most common oxidation numbers of all the elements. So better to memorize the common oxidation numbers of the elements. For example, for number A, we can find by the rule number 2, what was that? The rule number 2 was here. We can see that the lithium has an oxidation number of +1, and oxygen has number -2. So lithium here has the oxidation number of plus 1 and oxygen has minus 2. If we want to find the total oxidation number of the all the molecule, it has to be 2 lithium with the oxidation number of 1 plus 1 oxygen, and it is 0. For number B, for nitric acid, that one is the formula that in water it yields proton and nitrate. So we have proton and nitrate here. So we know the oxidation number of the hydrogen here, since it doesn't have any electron, it's plus 1, so it's considered as a proton. And the oxidation number of the nitrate here is minus 1. So oxidation number is minus 1. If we want to find for each of them, we have to know from rule number 4 here, for the hydrogen, the oxidation number is usually plus 1. For the number 4, no, it doesn't show this rule, so we have to see for the however, for the hydrogen is plus 1, and even number 3 shows that for the oxygen the oxidation number is minus 2. So if we know the oxidation number of the oxygen, which is minus 2, here we can find the nitrogen. So with writing a simple equation, we can find it. So here x equals to minus 1 plus 6, it would be plus 5. The oxidation number of nitrogen is plus 5. For the dichromate, the oxidation number of the molecule is minus 2. And we know for the oxygen, which is minus 2 again. So again, by writing a simple equation, we can find the oxidation number of chromium. Here we have so in this equation, x is plus 6 for the chromium. The next lesson, I will talk about all types of redox reactions. Follow me for more lessons. See you later.